Hello everyone, welcome to what will be pre-lecture 7. We're going to be talking a little bit more about solubility equilibria. And so we set up how to write a KSP expression to describe a partially soluble salt last class. And it would look something like this. Say we start with silver iodide, it can dissociate into silver plus, iodide minus, and we can of course write our KSP expression for that. And so we can do that, but say there was other ionic species dissolved in our solution. So for example, say sodium iodide was also dissolved in the solution. How would that affect the solubility of our silver iodide if we have a common ion? In this case, again, I minus. And so basically what happens, let me just go back here. What happens is our amount of iodide is going to be higher, and so that is going to decrease the solubility of our AgI. And we'll actually do some examples of this in class where we go through how does our solubility change when we have this common ion. But just conceptually, say we have this example here where we're looking at the solubility of magnesium hydroxide. Which of these species, if any, would actually cause a change in the solubility of magnesium hydroxide? And I'll give you a moment to think about that before I reveal the answer. And the answers are A and B. So with A and B, magnesium chloride, that can dissociate to form Mg2+. That would be one of our common ions. And then potassium hydroxide, that also dissociates to form hydroxide, which is our other ion. Notably, more MgOH2 is not going to affect the solubility of MgOH2 because this is going to be a solid, right? As long as our solution is already at saturation, basically we don't have to worry about there being more MgOH around because it's just going to be a solid. And as we know, solids are not included in our equilibrium expressions, okay? Another thing I want to talk about that kind of sets us up for another kind of equilibrium yet is talking about Lewis acids and bases. And so next week we're going to start in on all sorts of acids and bases, but I want to do kind of a preview of that that's going to be relevant for thinking about the solubility of partially soluble complexes. And so a Lewis acid or a Lewis base has to do with the donation or acceptance of electron pairs for two things coming together. So a Lewis base can donate an electron pair, and so if we're looking at this, something like ammonia has an electron pair that it can donate into a Lewis acid, which is something capable of accepting electron pairs. So in this case, it's ammonia, or not ammonia, it's aluminum, Al here. And when they come together, they just form what we would call a Lewis acid-base complex. Okay? Another example of this, we have boron trichloride, BCl3. This is a molecule called diethyl ether that has a lone pair that can donate into our boron orbital here, and again form this Lewis acid-base complex. And so why do we care about this? It is when we have this happen with generally a metal and a non-metal, we make what are called complex ions, which I will also call coordination complexes, where we have our Lewis bases, which I term to be ligands, bound around a central metal cation. So a metal with a positive charge, right? And that central metal is going to act as our Lewis acid, and then our ligands, our things around it that can donate electron pairs, are going to be our Lewis bases. And if we think about this just kind of out of the conceptual into an actual example, we can quantify this relationship based on another form of equilibrium, in this case Kf, and the F there stands for formation. So say we have silver plus, and say we have ammonia, NH3, those can come together, and ammonia doesn't actually have a charge, it's a neutral atom, right? Despite having a lone pair, can donate those lone pairs into silver orbitals, and we end up with AgNH3 This would be called, again, our complex ion or our coordination complex. And if we look at this, we can calculate K, how we would for any K calculation. We take our products, divide them by their reactants, raise them to their powers, and we get Kf. Something I want to point out with Kf that's going to be pretty different than most of the equilibrium values we see this semester is that Kf values tend to be very large, right? So this is 1.7 times 10 to the 7th. And so these interactions are very, very favorable, okay? And so how does this connect to KSP? We can essentially couple these equilibria, so we can make things that are insoluble, so things like silver plus, aluminum, copper 2 plus, lead 2 plus. We can make them more soluble by forming complex ions. Okay, so if we add a Lewis base to a solution that contains some sort of insoluble salt or only partially soluble salt, we can actually dissolve a lot more of it. And so if we return to an example we talked about last class, where say we have silver chloride with Ag plus and chloride being our products, we have a KSP value that's very small. If we add NH3, we know that NH3 is going to be something that is able to form this complex ion with silver, and then we can couple that Kf value that is very favorable. And so hopefully you remember from last week, when we have multiple steps in an equilibrium process, we can actually multiply together our two K values to come up with an overall K value. And so when we multiply those two things together, we get a new equilibrium for the overall process of 2.7 times 10 to the negative third, which again makes our silver chloride a lot more soluble. Just to kind of drive home that point, this is a table that contains Kf values for different complex ions. So things that would normally be insoluble are made more soluble. Things that I'll point out, you'll see like we have 10 to the 33rd here, just incredibly high values for solubility and formation constants. Okay. So we'll talk more about this in class. I hope that was informative. If you do have any questions, please let me know. Otherwise, I hope you have a great day.